Hey guys, your boy Chill here. Welcome back to C Multithreading. Today we're going to be talking about the idea of unbalanced workloads. And in order to do that, we're going to rearrange the setup we have for our data sets that we're working on. And we're going to add a bunch of ways of manipulating how we set up those data sets and how we can measure the time taken on the data sets. And it's going to give us some good insights to work through going forward. So, what do I mean by unbalanced workloads? Well, if we look at our current setup, we've got 4 arrays, 1 array for each worker. Those arrays are logically broken up into sections. We call them chunks. And what we do is in every phase of our processing, each worker will process all the items in its chunk. And when all of these 4 have completed, only then can we proceed to the next phase. And that's kind of simulating the idea of something like, let's say, a rendering engine or a game engine. One thread can't just work through the entire work set, right? It can only work through the data for the current frame, and then when that frame is completed, we start the new frame, and then we're able to work on the data for that one. We can't really work ahead throughout the whole data set. In this case, the data set would be all the processing from when you start the game until when you end it. You can only really work on the current frame, and once all the threads of that frame have been done, it can be submitted, and then you can start work on the next frame. So that's the idea there. And the work sets, they are the smallest item of work. A single work item, in our case, is just an integer. And we do some processing on the integer, and we sum up the results of each of those processings into a single sum. And then at the end of the day, we gather all of those results from the 4 thread to get our single answer. Simple enough, right? Now, what I want to do, the main thing that I want to accomplish here now, is I want to make it so that our individual work items, they're not all going to be identical in how much time they take. Some will take longer than others. And this is a more realistic scenario. Usually when you have, a bunch of tasks to do and you've got threads working on those tasks all won't take the same amount of time. No matter what those tasks are, they're going to be asymmetrical. And another thing is, normally you won't be able to compare them and say, oh, this task is going to take twice as long as this task. It won't be easy to make that determination ahead of time. You'll only really know how long the task takes once you finish the task. That's going to be a problem. So I want to simulate that scenario, and I want to instrument it. I want to show off how it affects our total work time for completing an entire chunk. And in order to do that, we're going to have to do some coding. So that's what we got on our plate today. So I got a few notes here. Let's just go through them right now. So what is my wish list for the stuff that I want to code up here? So first off, our work items, right now we have integers, but we're doing mostly like floating point calculations on it. And I did some dumb bullshit where I basically normalize the input integer value using numeric limits to get a value between 0 and 1 and whatever. But so let's not do that. Let's just put them as floating points to begin with, or doubles to begin with, and work with them like that. Why not? Not a big deal. And put them in the range that I want to work with. So when we generate them randomly, we'll generate them between, maybe like -1 and +1. Because we're going to be doing, again, probably like sine cos on them, because it's an expensive operation. We want to make it expensive. And that brings me to my next thing. I want to make the individual work items heavier, because right now all the work item does is it does a sine, it does a cos, it does some floating point, what do you call it? Not translation, but conversion. And that's not very heavyweight for a single work item. It's not realistic. Work tasks or whatever that you work with in threads, generally you work in a larger granularity than this small potato stuff. So we're going to beef up how much every work item takes. So we'll make our data set smaller, but we'll make each item a lot more difficult, a lot more time consuming. And what we're going to do is, in order to simulate the situation where we have, work items that take less time and work items that take more time, is we're going to give each item a way of signaling whether it is a heavy work item or a small work item. We could make it where it could be like a range of values, but instead I'm just going to be like, a work item is either normal weight or heavy weight. There's just two different states of it. And that lets me explain this, which is to say, I'm going to make the work items heavier, but I'm going to parameterize it so I can do different experiments. So just by changing a single value, I can change how heavy the normal work item is and how heavy the heavy work item is. So I want to make things more parameterized so I can do different experiments a lot more easily. That's one theme of the things I want to do in here. I'm going to rearrange the way the workload is set up. So right now we have it set up where there's one array per thread, and that is logically broken into chunks. And then the master thread, which divvies out the work, basically calculates the span for each one of these chunks and, dispatches that to each worker. So what we're going to do instead of that is every chunk, let me just get a new layer here, and we'll turn this layer off. So now every chunk, that's the wrong color, of course it's the wrong color. Yeah, we get there. And now I'm not on the layer anymore because Control Z in Photoshop just loves to mess my life up. So stupid. Anyways. Okay, so now this is going to be, chunk 1. And we're going to divide this up let's say into 4 sections, and that's for each thread. So each thread will work on a different section of the same array, and they'll just be divided up like this. And every different chunk will be a separate array. So now the chunks are separated from each other in separate arrays, but each chunk is divided logically and dispatched to the different threads, if that makes sense. And that is going to let us do some stuff in the future. So we're just basically looking forward to what I want to do in the future and rearranging things now to suit that. So yeah, flatten 4 chunks into a single array. That's this idea here. These 4 chunks, which are distributed across 4 arrays, are now going to be in a single array. And we're going to have an array of those chunks instead of array of data sets per worker. We want to be able to control the size of the chunks and the number of chunks in the total workload, again with different variables that I can set either just in code or with a command line switch, whatever. And here's a big one. We want to do a lot of measurements. We're going to measure times. We're probably going to spit them out as CSV files that we can then open up in like Excel or something and look at. So I want to measure the time taken, per chunk. I want to measure total time taken per thread. I want to measure the time each thread takes to work on its own section of a chunk. I possibly might even want to measure the time taken for every individual item processed. That'll make a very big CSV, but we might do that. I'll think about it as we're going through. And of course, we want to measure the total time. We're doing that right now. And I also, especially for these like per chunk things, I want to show how many heavy items were processed, because we're going to be looking at distribution of heavy items and how that affects the total processing time. So it'd be nice to see that in the CSV. So we're going to be, spitting out a lot of time data and also a little bit of data about the workload. And I want to be able to control the number of threads, because right now that's pretty hard coded. But I want to be able to show, okay, so for this data set, how would it look if it were processed by a single thread? How does it look when it's processed by 2 threads, by 4 threads? That'll be an interesting comparison to make. And this is very important. I want to be able to control the distribution of heavy workloads. So are they going to be, well, let's go back to this. And let's say heavy work items represented in red. Do we distribute them equally? So every, section, every thread, that every worker gets an equal amount of heavy work items. Versus, what happens when all the work items are like stacked up in just one worker's queue, and the other ones just by random get lighter workloads. Maybe they only get like 1 each, and see how that affects the total working time. So those are the kinds of things that I want to code up in this bad boy. That's going to take a little bit of reorganization of the code base. All right, looks like we got our work cut out for us. Let's get started here. But one little note that I want to make here, my original code here had a little bit of a flaw in it that will be a big problem moving forward. We're using a random generator to generate 4 data sets here. The problem is that the 4 data sets that we generate, while they will be, pseudo-random in themselves, they will be identical to each other. We will get 4 identical data sets. Can you see the reason why? And the reason is because generate takes, as algorithms tend to do, it takes its parameters in by value. So when we take in this random generator by value, it's going to copy the initial state 4 times, and it's not going to modify this original object. So you're going to get 4 identical seeds generating 4 identical data sets. And that's not, in general, that's not what we want. We might want that special case sometimes, but in general, we want to have different data sets so that we can see how that affects the total runtime when we have, asymmetry in distribution of the workload. So that'll be something that we want to look at. But right now, let's just start off with a little bit of coding. So we're going to struct task. We're going to create a structure for a task item, and we're going to do double value. And we are going to do, what are we going to do here? Let's do bool heavy. So we got a couple values in here. One to check to see if it's going to be heavy or not. Now I'm just trying to think of how I would like to do this. I think we'll put the process function just as a member of this struct, unless I can find a reason why that's a bad idea later on. So void, no, let me think here. Yeah, so we have function here that just runs over an entire chunk of data and processes it. But let's make the processing of a single item, let's make that a member of task. So we'll get it to return a double. And it's going to just be process const, doesn't take anything in. And what we will do for the processing, because this is interesting. So there are 2 cases. There's the case where it is a heavy data set, and then there's the case where it is a light data set. So first off, if heavy, we do the heavy case, else we do the light case. But I think the actual nature of the processing will be the same. It'll just be a loop, and the number of iterations in the loop will determine if it's, how heavy or light it is. So let's do I'm this all caps annoys me. I'm just gonna get rid of it. So we'll go chunk size, and then chunk count. So that's how we're gonna define our data set sizes. Size of each chunk and the number of chunks that we're going to be working with throughout the entire run. Now here we want to do, we'll do light iterations and heavy iterations. And then when we process, we're going to do for size hit my caps lock. Size t is equal to 0 as long as size. Let me think here. Const auto total. We'll just go iterations is equal to heavy. So if we're heavy, then we'll do heavy iterations. Otherwise, we will do light iterations. There we go. So as long, I guess we need a variable here. We'll just do I. Good old I. As long as I is less than iterations, I plus plus. And we're going to do I iterations, I guess total, sum, double result is equal to I guess that would just be equal to the initial value. And then we'll do result is equal to sine cos result, return result. Okay. So here we'll get different workloads depending on whether we are a heavy or a light workload. And we'll figure out how we want to initialize this later. I don't know what values would even be appropriate for this, but let's say the light is going to be 100 iterations, so that'll make workloads about 100 times heavier if they were all light. And then for heavy iterations, let's make heavy, I don't know, like 10 times more powerful than light to start off with. So chunk size, how big should each chunk be? I mean, if we said each chunk was 100 items and, we had 100 chunks, I don't know. It's probably mean a little more than that, but we'll tweak the numbers later on when we get some concrete data out of this bad boy. This is a good start, I guess. But yeah, here is where all of our experimental settings will go into. All right, this one we might remove it or change it. We'll see. Generate data sets. Now the end game for this is we're gonna be able to have different functions to generate different kinds of data sets. But to start off with, I guess we can just have a generator for the simplest version. First, we have to define the shape of our data sets. So I think because our chunk size and our chunk count are both const expr, we might look at an array of arrays, maybe. I'm just thinking of like if there's anything wrong with that. I mean, I guess having a vector of arrays makes it easier to return things, possibly. Depends on the context, right? Because you're returning just a few pointers rather than a big chunk of memory. And also it makes sure that things will get on the heap so that we don't inadvertently give ourselves a stack overflow. So I guess a vector of arrays is fine. The vector will be a vector of chunks, and each array will be the data set of chunks that will be shared across however many worker threads we have. We can put in here, just when I remember it, worker count. So we'll start that generally to be 4, but we could play with that to do different experiments as well. So the size of the array, the value of the array will be an array of tasks, and the size of it will be chunk size, because each one of these arrays is a chunk. Now, we would like chunk size to be a multiple of our worker count. Otherwise, it's going to be hard to divide equally up the chunk for different workers. So let's do chunk size should be greater than or equal to worker count, and static assert worker count mod chunk size equals 0. Just a couple of little, what's your problem? Something's wrong. Static assertion failed. That's the wrong way around, clearly. Thank you for telling me. Worker count. There we go. Beautiful. Okay. So we're just going to keep going on to this. Task, chunk size, generate datasets. Okay, so we're going to generate a dataset. This random engine seems fine for me. I think we're going to need a whatchamacallit. What do you call those things? Uniform real distribution. I don't know the difference between uniform real and uniform real distribution. What is the difference? I could look it up. It's strange, like when I go look up uniform real, it just gives me something on Boost, and I don't know why that's in here. But anyways, I've never used it before. So we're just going to use uniform real distribution. That's our distribution. What is your problem? Don't know what your problem is. Probably you need like a range of values, but I don't understand why you just say error type there. It seems a little weird. Anyways, let's go from negative. Oh, wait a minute. I think I know the problem. Maybe it should be double? I don't know. So negative 1 to 1. Seems about right. All right. Now, the other thing is we want to generate the heaviness. So we want to decide, when we're going to be a heavy boy. There's probably a distribution for that, right? Like is that a Bernoulli distribution? Kind of. It is indeed Bernoulli distribution. We can instantiate it with a P, and that's the probability of true or false. It even returns a Boolean right away, which is like, that's beautiful, right? So we just want like our Bernoulli, our Bernoulli. So std yeah, there we go. Bernoulli distribution. Dist and const expr. This is probably like a double, right? No, I don't want to say P. I want to say probability heavy is equal to. So let's make heaviness be like a 0.02, boy. So then we go probability heavy. Okay, so now we got our distributions. HDist, VDist for, kind of looks like it's vertical and horizontal. It's not. It's value and heavy, but whatever. Now, we're not going to be data set size here, obviously. We're going to be like chunk size. Give me a break. And this should be worker count. No. Now, that's old meta. New meta says this should be chunk count. I'm just thinking, like, if I use square boys here, is that trying to initialize it with a value of 4? That can't be, right? I'm just going to use round boys. Yeah, we're just going to use round boys in here. We'll figure it out. Okay, so we go over each one of these data sets. Do we? I mean, yeah, it doesn't really matter. This still works the same. So this is not going to be data sets. This is going to be chunks. And we're going to go, over for each chunk in our array of chunks, our chunks, we are going to generate. We're going to run generate on that, but we're not just going to use RNE directly. We're going to use our distributions together with our old pal, the structure. So we would like to capture everything by value. No, that's not how we want to live our life, right? We want to capture by reference so that we can get different data sets. We don't have Groundhog Day syndrome. I don't want this one, obviously. I want this one, obviously. Now, what we're going to do is we are going to return our good old boy. Probably helps if we just say that we're returning a task here, right? What's your problem now? Oh, you want this because you have... Okay, I get you. Whatever. You know what? Screw you then. I want to omit my round brackets like a cool guy. So I'm going to do this. Return task dot value is equal to vdist rne comma dot heavy is equal to hdist rne. Yeah, there you go. What is your problem? That's not right. It should be a task, right? There you go. Compiler, IntelliSense, always got your back. Always got your back. All right, and then we just return our chunks, and we're good to go. So this is one way of generating data sets, the most vanilla way, I would say. And I think that's a good start there. All right, now we'll eventually delete these do biggie and do smally functions, but I'm going to keep them around because I might want to refer to them. But I think maybe we'll just tackle things on the level of our active objects. We got master control, we got worker. Wait for done, signal done, int worker count. I feel like worker count is not going to be necessary because we have the, I mean, it's just a constant expression, but maybe not. Maybe I think worker count was used to do something. It's been a while. Well, no, that's done count. Worker count was always it just stayed the same. It was static, so that can definitely be removed. Shared memory done count, yeah. Dunesies is gonna be, so I mean, can I just do that? I mean, obviously not there because, it doesn't make any sense, but can I do it here? Yeah, okay, good. Signal done. This is actually, okay, so this is a funny thing. In the previous video, there was a comment that this is a race condition, and that is technically true, yeah. This is a race condition, probably not a data race. I guess it depends on what architecture you're working on. And it's not an issue on x86 for sure, but it is technically not well-formed C++, so we should do this comparison under the mutex to make things perfectly cromulent. Now, it's not a big deal either way, but generally you don't want to signal while you're still holding the mutex because the other side could wake up while you still have the mutex, and then you have a collision, and that just wastes everyone's time. So what we could do for that is we could do, bool needs notification false, and then we would just do here needs notification true, and then after we're done this part here, we just check if needs notification. You son of a bitch. Okay. If needs notification, cut this out, put it here. I hate everything. X, why is Control X and Control V so close together? Anyways, or Control C, whatever. Yeah, so we'll just, under the mutex, we'll do the tests. If it's whatever, we'll set this, and then after we release the mutex, if we need notification, then we'll notify. There you go. It doesn't really change anything for running on x86, which is the only code that probably anyone's running this on. But still, to be correct, we should be doing it this way. We should do that comparison under the mutex. And if you want more details about the discussion there, you can go back to the previous video and check the comments, because the guy posted there and I replied there, so whatever. But this is how to fix that. All right. I mean, obviously we don't need this anymore. Now, people were often commenting. They're saying, Chili, you cut too many things out of the video. A lot of times I'll just code off screen and then talk about it. And they're like, I want to see your code. Well, now you're getting it. Now you're freaking getting it. So hope you like that, because this isn't going to be a short video by any stretch of the imagination. All right, so we are signaling done. We are waiting for all done. I mean, this should be fine, right? We're going to need to do more changes, but I'm just changing what I see right now as needs to be changed, and then I'll take it from there. Set job. So P out. So what are these P outs and what are they doing here? We got to go back to here. Where is set job being called? What is P out? So we got sum. All right. So I made these value things to be spaced far enough apart so that they don't participate in false sharing, which is fine. That was to prove a point. But what we could also do even better I'm just trying to think here now. Like you want to space out the memory that the different threads are going to work on enough from each other. One thing that I'm kind of a little worried about now, just thinking about it, is if I put the workers all in the same, vector beside each other, one after another, is there a case where some of these shared memories could end up in the same cache line and also just, cause me a little bit of a headache? And I don't think so. I mean, honestly, I don't know the size of all of these things. Obviously, I mean, this is a size T. I don't know what the size of a condition variable or a mutex is. It's an interesting problem. You want to space, if you've got all these like shared, because this is obviously going to be stuff accessed by different threads. We want to make sure that these are spaced out between each other enough. Process data set. Yeah, so the only real thing that's going to be accessed when the threads are doing their main work, the only thing that's going to be accessed repeatedly is the value. So if I put the value in here, we just got to make sure that they will be on separate. Yeah, and I mean, there's so much here. They're going to be in different. So it's not a big deal, and I didn't really think it was going to be, but so yeah, we keep the span. P output, instead of P output being that, it's just going to be double. Accumulation. Sure. Why not? I mean, it shouldn't be F, it should just be that. Bool dying false. Okay. So we're going to accumulate in here, so now we won't have to take in the P output. So set job will just set the data, will not set that. And in here, we're going to do input is equal to data. Accumulation will reset the accumulation anytime a job is set. And notify. So that'll be simple. Kill. Master, sure. Now here we're using P output also as a kind of state to tell whether we're working or not. So we can use input for that same, because when we finish we set it to an empty span. So if we do input dot so P output not equal to null pointer is the same as asking if our input is not empty. So we want to wake up if our input is not empty, or if we're dying. In either of those cases, we got to wake up and do something. All right. Process data set. This might be replaced with a member function. There was a reason to pull it out into a separate function before, but we're going to delete that code anyways. So if we put that as a member function, oh, we could just put it right in here, but we might as well separate it out just for tidiness sake. I mean, you just loop over the span and then you run the process, so it shouldn't be that complicated. For, let me think here, const auto and task in input accumulation plus and equals task dot, no. What's your problem, doggy? Okay, obviously span of int is not good. We need a span of task. And that's going to change some other things here. What is it going to change? Well, I mean, this is, we just replace this with a process data. This doesn't make any sense, but we should change p up. No, we don't want to change that to null pointer. We'll have to think of a way of getting at the result in the accumulation, but that shouldn't be too hard. Plus and equals task dot process. There you go. So that's simple enough. Input is equal to data. It's not going to be a span of int. It's going to be a span of task. That fixes that. Double get result const return accumulation. There we go. All right, that's looking better now. We'll just call our function your do experiment, and we'll just kind of pull in stuff as we see fit. So I mean, we don't need this value bullshit anymore, so let's get rid of that. I mean, might as well keep the timer for now. So we'll keep the generate datasets. We'll keep the timer. Datasets might as well be constant. We're not going to do anything with them. I might as well just delete stuff as I copy it over. Worker count. Now that is not necessary because we have that in our settings up at top. Master control, sure. But it doesn't need to take in any parameters anymore. Get rid of that. So we have a vector of unique pointers to workers. So then the workers aren't even going to be, particularly contiguous in memory. But it depends exactly on how the heap is set up, how close to each other. But again, it's not going to matter. We're not going to have some false sharing problems. Is less than worker count. So we create the master control. We create the vector of workers. The subset size is not going to be necessary. So now we're going to loop. We're basically going to loop over chunks. I use different terminology here. I thought I used the terminology chunk, but now I'm saying it's a terminology subset. So we're not going to use the terminology subset anymore. Again, we're going to use the terminology of chunks. There's chunk 1, there's chunk 2, or chunk 0, chunk 1. And then within each of those chunks, we're just going to have, I guess that could be considered a subset. I don't know. a workload. I don't know what I name things anymore. But we have to give them names, otherwise we're just going to confuse ourselves later on. So this is a chunk, and this is a subset. That chunk is divided up into subsets, one subset for each worker to work on in our current situation, which will differ. So we want to loop over chunk count. I'm going to call this index chunk, I chunk, just because it's more useful than I and J. And here it'll be very simple. We just do I chunk plus plus. Now, we want to divide that up into a number of subsets. So I subset, as long as I subset is less than worker count, I subset plus plus, and then worker pointers at I subset set job. Now we don't have to pass in the sum because that is stored internally to the worker active object. Datasets is not a thing, is it? Let me think here. We should rename, well, first of all, we should move this over here because this is where stuff is actually going to be done. Second off, we don't call it datasets now. We call this one chunks. I'm just thinking to myself now, do I even need this bullshit? I could just replace this, correct me if I'm wrong, with a const auto and chunk in chunks, and these are chunks, and then subset is, we'll have to do this one with numbers, and then worker pointer at I subset set job address chunk so we can go up here and we can say chunk size, chunk count, worker count, chunk size. Const expr size t subset size is equal to chunk size divided by worker count. There we go. I like that. That's pretty good. That's pretty smart. Now we do, let me think here. Address of chunk at I subset times subset size. And then in here, the size of this subset. So the start of the subset here, size of the subset here, std span. That's a pretty big ass number. Std span task, very big number. No user to define conversion from const to non-const. Okay. So that's fine and good, and we love it. We can fix this. This is just a little bit, this is when you pay the piper. I love being correct with my constness, but sometimes it's like, yeah, no, be better, be a better programmer. And I'm like, I don't want to be a better programmer. But that should be good now. We have determined that, wait, what's your problem now? Error type. Okay, well, that's fine because this is not the one, this is not the thing. The thing is here. And now it's fine. The compiler says, okay, you have proven yourself worthy. Okay, so then we can get rid of this. And So now I'm thinking, do I want to just allow every worker to carry over the accumulation between phases, basically, between chunks? It's a little different than what I was doing before, maybe, but I don't see a reason why. Like, I don't see a reason why I would want to put, like, make an array of sums external here, and then after every chunk, accumulate into each of those individual sums, and at the end, sum them all together. So in that case, if we're just going to carry over the work between chunks, what we should do is we should not reset accumulation when we set a new job. We are initializing it here, so we just initialize it once at the very beginning, and it will just keep that between chunks and keep accumulating it. And that's fine. And then go back to where I was here. And then we can just take this. We could be like a little sexy. You want to be just a little bit sexy? I'm feeling a little frisky. That's usually famous last words, and I try it, and then it doesn't work. And I get angry, and so I keep trying, and then like three hours later, I'm like, why did I try to get so freaking frisky? Just write a loop or something. Anyways, accumulate, not in there. Okay, fair enough. It's a little known trick there. Did I not include algorithm? That's weird. Well, let's do it anyways. Algorithm. And let's include, what's the other one? Numeric. That's the trick. You think accumulate is an algorithm. It's going to be in algorithms. No, it's in numeric. That's a rookie move. Now, is it in ranges? Okay, so ranges doesn't have accumulate for whatever reason. Jerks. Do I want to do it without ranges? It would be a lot sexier with ranges. I could do a sexy, what do you call it? Is there another one? Ranges. What's the one that's not accumulate, but it works like very similar to accumulate? Reduce. No, it's not that. I'm just gonna check. This is the spiral. This is the beginning of the spiral where I spend 3 hours trying to be cute when I could just do something really simple. Let's get the spiral started. I'm gonna look. Google search for ranges accumulate. Okay, well, this answers my question pretty. Why didn't accumulate make it into ranges? Not made obsolete. The reason it does not be included is simply a matter of time. Yeah, so they just didn't get to it. They're just being lazy bones. Okay, so, I mean, this is why we can't have nice things. Because, I love me some projections. If you don't know what that means, then don't worry about it. But anyways, we're just going to do like the normal broken ass accumulate. Woke, broke, and bespoke. Which one are we? We're broke. We're definitely broke. So that's going to be worker pointers that begin, worker pointers that end. Value is going to be 0 to begin with. And then we need our reduce op, which is annoying because there's no IntelliSense for this. So now I don't know what the signature should freaking be. But now, you might be saying to yourself, Chili, why don't you just write a freaking just a range-based loop and do this? Listen, Listen here. You know what? Fine. Fine, you win this time. If we had ranges, I would do it with ranges. But because we don't have ranges, I'm going to say screw you guys. For each const auto and W in worker pointers. Well, now I need a thing to accumulate into, don't I? Double answer is equal to 0. Don't put the F there. And then answer plus and equals W pointer to get result. So I should probably name this result. Final result. There we go. There we go. Are you happy now? Are you happy now? I didn't indulge my what do you call it? My fetish for std algorithm this time, and this time only. Okay, there we go. And then we should kill the workers. I feel like a destructor on these guys should just do that stuff, but I don't feel like working out how I want to do that. Yeah, it just doesn't appeal to me right now. But there we go. I'll leave this in here just because I might use this code later on. And do experiment. I mean, I could just look at the git for this code if I really, so I'm just going to get rid of it. It's cleaner. Yeah, okay. Okay. Now, do biggie. You are dead to me. And generate datasets, we need that one. Process dataset, you are dead to me. And this is all we need, ostensibly. Think this is gonna work? What is the actual do experiment doing here? Wait for all done. Oh, I mean, it has a chance of working, right? How often do things actually work like the first time? 10% of the time? Well, it didn't even compile, so fair enough. Must return a value. Return 0. There you go. We're not using the return value for anything, but who knows? We might use it in the future. Okay, so we succeeded. And what did we succeed with? How much time do we got left? I've already got an hour in this video. And believe me, I'm just getting started. This is like an experiment. People keep telling me, Chili, we don't like it when you cut things out. Show us everything. Well, now you're going to get everything. And let's see how you like that. 69. Nice. All right. It should, obviously every run should do the same because we're not doing anything about seeding and we don't want to. We want it to be reproducible. Now, so it takes doesn't take very much time at all, does it? So we could increase the chunk size by 10. We could also increase like the I want to see if I increase the size of the heavy iterations, if it has an actual real effect on the runtime. But since they only make up a small portion, shouldn't be a huge change, right? And also we're running in debug, which is not good. Let's increase the chunk size by 10. We'll do the same chunk count. So if I increase the chunk size by 10, well, let's change the release. Always good to change multiple things at once so you don't know the effect of any particular one. We can run this. 69482. Interesting. It's like almost the same. I don't trust that. If I increase the number of chunks, it's like almost the same, only it got 10 bigger. So if I do 100 chunks, CM 4.2. Right. And if I make it 10 times bigger, it just the value just gets 10 times bigger? Does that seem right? If I make it bigger, you're going to get more random data, and so it should be like much more different. It just seems wrong to me. I'm also like thinking to myself now, with like problems, rounding problems with double values, when the results are very tiny and the whole thing is very large, like, you know what I'm saying? I don't know, man. Like maybe there was a good reason why I wasn't using doubles in my data set and was instead converting when I was doing my calculations. This is what I'm trying to say here. And if that's the case, then maybe I should just an integer. But then we're back to the thing of where I have to like, you know what I'm saying? All right, I'm back on my shit here. What is this? Identify. Yeah, okay, that's fine. So we're gonna change this back to ints. And so this is going to return an int. I'm just seeing how I want to do this. I think it was unsigned before. I can't remember. Anyways. So, yeah, we'll make this unsigned int. And we got limits in here. Okay, so how do we do this? So we get iterations. Okay, so this is where intermediate, and this will be that, and this will be that. So we're going to convert this into a value in range. How do we do that? We'll take the value. We'll convert that to, do we convert that to a double? Why not? Yeah, why not? Double value divided by double std numeric limits unsigned int max. Yeah. So that'll give us normalized between 0 and 1. Two times that minus 1. That'll give us a value between +1 and -1, more or less. Probably. I don't know, man. Then we're going to do our stuff with that. And then when we want to return our result, we just have to like do the opposite, which is to say interesting conundrum here. It'll work. It'll work somehow. Doesn't really matter. What we do is we convert it back to a 0 to 1 thing, which means we do intermediate plus 1 divided by 2. Yeah. Does that make sense? Yeah. Yeah, that makes sense to me. Then times double this. Convert that to How's that? Seems good to me, right? That's perfect. That's a beautiful thing. We could just step through it to make sure it makes sense, but I think it's pretty good, right? Can't be that bad. All right, so that means that this stuff is going to now work with integers. What does that change? Now you should be a uniform int distribution. Do I need a uniform distribution if I'm just generating numbers? What does this thing output? I mean, I don't even know what this thing is meant to output. Unsigned int. Probably. Because that's what it is in the template parameters. If that's the case, then you can just take a hike. And you can just do that. This returns. No, what is the unsigned int? Yeah. Good. Yeah, that's fine. Okay, now, what else? I mean, there's got to be something else wrong here. Obviously, this should be... this should be an unsigned int. 0. Let me see here. This returns unsigned ints. That's good. Unsigned int. I'll do that. That should be unsigned int. A little annoying that it doesn't do IntelliSense. It'd probably give like at least a warning if I tried to compile that, but chunks. And this should be an unsigned int. There you go. All right. Seems better now. Warning. Yeah, so here you go. Like this one. Which is not a big deal, but there you go. So now if I run this, result is 422 and a 60 on the end. And now, it's going to be like a different number. Because things are, you know, they're like 42296 on the end. Interesting. For only 422 million. 42284. If I increase the size of the chunks. It's just 10 times bigger. How is that possible? I gotta be doing something dumb. There's gotta be something like really dumb I'm doing here. But I'm getting this by... Like it's got to be like every operation is like yielding the same result, and that's why when I increase the chunk size, it just multiplies it by 10. Did that take too long? How long did that take to process? Yeah, no, that took like nothing. So I can add another 0 in the end, and it should take 10 times as long. Yeah. Well, the value did change in this case. Like the top of it changed, but I think that's just because it overflowed, right? Yeah. We take it down. blah blah blah. Yeah, 6960. 36960. Now if I take it down another one, $3,696. Yeah, it just gets 10 times bigger if I increase it by 10. But we have random data doing random stuff. So there's something wrong with my calculations in here, really, is what it boils down to. But what is it? What could it be? I guess I'll just have to like step into it a little bit, see what's going on here. What do we got here? Iterations. Now, one of the problems is we've got 4 threads doing this, which is a little annoying. 100. Makes sense. 100, 1,000. So the intermediate value, negative 0.93, negative 0.99, negative 0.51. So we're getting, as expected, we're getting lots of different values, which is good. It would be annoying if they started off at basically the same value. Now, what happens when they all reach this point? Do they all end up at the same value? Because doing this iteratively just kind of, I guess it could converge to something. I don't know. I haven't thought about it too hard. I just picked them because they just seemed like decent enough random. 0.6948. Okay. 0.6948. Continue. 0.694. Okay. So I think I see the problem here. And that is if we do repeated sine cos enough, they just all converge to the same value, and it's kind of annoying. It might not completely invalidate my approach here. The value itself doesn't really matter, but it's nice to have some chaos or some entropy in this so that if I change something a little bit, we get a completely different answer. And that kind of would help, because then potentially small little errors to do with like race conditions could throw off the result completely, and it would throw up a nice red flag. But if the results tend to like converge, that might not work as often. I don't know. It's just like a hunch I have. So at the end of the day, I don't want my random data to always converge to the same result because of the operations that I chose to perform on it. So I'm going to have to rethink my operations here a little bit. But it seems like a good start, at least on this code here. And I will, I'm going to continue on with this later on, and I'll record what I'm doing there as well. And once I have this approach all set up and I'm able to gather the data, I will probably record a shorter video. This is my idea I've just come up with right now. I'll record a shorter video that basically just goes over the results of all this work. And that's the video that will make it into the multi-threading playlist. And in that video's description, I will put a link to this video and a subsequent video where you can see the details of all the stuff that went into getting those results. So I'm thinking that might be a little approach that I'll take to content for the next few videos at least. See how people like that. But before I'm done with all the results, I'll probably just release this video. So if you wanna watch the process semi-live as it's going, you can do that. Or you can just wait for the final results video to come out, and then if you watch the results and you're interested, you could, then people could click the detailed videos to see what went on behind that. But anyways, I'm just rambling on now. I'm just talking inside baseball. But I need to stop this and do some other stuff now. So I'll stop the video right now. And when I come back, we'll continue on creating our experiment code here and making it fulfill all of the requirements later.